Good afternoon. Welcome to EuroBSDcon. There's an announcement from the organizers. Please look to your right, and if there is or if you're on that side on your left, if there is a free space
I would do without
to either side of you, please move over because people will be arriving late for the session. I see people still arriving, but we're trying to keep the schedule here. So please welcome Martin here, who is an OpenBSD developer who's been taming the network stack. So take it away, Martin.
Thank you very much. So thanks you for being here. As Peter said, I'm an OpenBSD developer. I'm a bit late into the party. That's an interesting fact for the talk I'm giving right now, because I'm mostly working on what I'm going to talk about is about code that is older than I am. As you can see with the name of the presentation, I'm going to talk about network. What exactly? I found a really funny name that comes from a joke that I would explain a bit later. So taming those OpenBSD network stack dragons. For those that don't really know me, I spend a lot of time in OpenBSD kernel as a day job to the network, and during the night working on USB, Power PC, or some different stuff there and here. So what I'm going exactly to talk about, what are those dragons that, well, I'm mentioning in this slide. The first, or maybe the easier way to present or to introduce you to those dragons, it's to, let's read a command that you can find if you're looking at the network code inside the OpenBSD source tree in the kernel. That's an interesting question. To adapt my talk, I want to know maybe how many person are familiar with the internal of the BSD networking subsystem, or maybe are coding. Maybe can you raise your hand if you know something about that? Okay, so I try to adapt the language. So the comment I was talking about, you can find it in this file, and as you can see, when we are afraid of something, we call it a dragon. A dragon is a legendary animal. I don't know how many of you have already seen a dragon. I didn't, but the effect that dragon can do, at least in a kernel, are quite terrific. This talk could have been named "How to Badly Break Your Network Stack." It comes out of a joke that I say, well, that's really interesting stuff that I don't know how many people know about the BSD history, this design. Why do you want to break that? Why do you want to change that? That's a really interesting question. So I tried to do a talk here in 45 minutes. A lot of people already told me that if I want to explain what I did and how many times I break the network stack, it wouldn't fit in one talk. So I'll try to be short here, but don't hesitate to ask questions to have further details. So what are the motivations that leads me to look for those dragons, those creatures that are in your 30 years old, a bit more than 30 years old operating system in this code there? That's the first point of the agenda, right? After that, since we are talking here about network, I don't know how many of you are familiar with the notion of addresses and routes. Is it the right place to talk about that? Well, you would tell me. But I will introduce that and specifically how, from my point of view, as a network developer, as a kernel network developer, we choose, or at least I was told that the BSD people, the guy in Berkeley, decide to represent them. That's really interesting to understand how they are represented. Because since I'm looking into this network stack, and I found a lot of dragon there, I want to understand where they are living and why we could find some dragons. Then the change that leads me to break stuff, the change, why would you like to break stuff? What kind of change can break stuff? What kind of change did we do on OpenBSD that none of the other BSD did, that we found some specifically complex design decision on the original BSD kernel in the network stack? Where those changes led us That's the point of now. And finally, I will conclude about this experience, which represents about 1.5 years of work. So feel free to interrupt me if you have some question, if I'm not clear. As I said, there's a lot to say, but I think we can manage to see all of the slides. So first point, the motivation. What's bring me here? To talk about those dragons, right? Well, the first point is obviously to give a talk to the EuroBSDcon. That's what every BSD developer are working for. You might like, as I am, to enjoy code of the 80s. I was born in the 80s. After this, the code I'm touching has been written, and well, it's interesting. I was not particularly interested in history. Well, it's interesting. But why I enjoy this code, or I don't enjoy this code, it's because I would like to make it easier for other people, for myself, to run it in parallel. I don't know if it rings some bells here. Computer used to have one central processing unit. Now, as a day job, my employer wants to sell router based on OpenBSD. He wants to sell router that are fast. That's something, well, I don't know, people are interested in fast software. And one of the ways to make it faster, at least that's what they told me, that's what they hire me for, is to execute it on multiple CPU. So what I'm writing here on the sub-point of making it run in parallel is that the motivation, and the important motivation that leads me to make the change in the network stack is to be able to make it easier to simplify the code that we want to run in parallel. And I will be focusing on the forwarding path because the company that makes router are really interested in those performance. It's quite a long talk. It's quite a big piece of code, but it's interesting. I'm precising on the second part that I took an approach that I wrote on top because other developers are approaching this question of running code on multiple CPU. And it's interesting when we work in software development if we work as a team, so we share the work. Some people as a position of the top, I could say the bottom, that are addressing or interested in the problem directly from the close to the hardware, so from the driver system, allocation mechanism. I will look more at something which is even for people that don't really do operating system development can understand. It's basically the top, what we call IOCTL. That's what's the process when they enter the kernel to do some configuration change, what kind of data they want to write, modify, and of course the code that we run when we want to send a packet from one interface to another one. That's what I mean when I write IP forward path. Now, an interesting point about this work is, I mean, when you think about a strategy that you have to deploy, that you have to change to make it run in parallel, or at least to help it make it run in parallel, is that a lot of the tricks are also true for plug-and-play problematics. That means that when you plug an interface, that I appear to work on USB too, so I know what I'm talking about, that when you plug an interface and remove it, somehow the kernel state change, that you were representing an interface, your computer in the memory is some information, and you're removing that. How do you manage to maintain the integrity of your kernel? It's similar, and I will come to a bit more detail later. And the last point is, I think, interesting to explain it for people that are not really familiar with the process development on the OpenBSD community, is that it's probably impossible, at least even if with the team of people I'm working, to test all the change. So when we have such huge code base, and I think that Ted was saying something similar in the previous talk, that you can only find all the bug or at least a lot of the bug when you're really running the code in production, or when you're really running in the use case. That sure, your regression tests help you. Sure, you can have a test setup, and you should. But we want it to commit it early so that people can try it. It will find bug. It always broke something. It's reverted so that people can still use OpenBSD. Otherwise, they don't trust us anymore. It's a broken system. How can you use a current system which is broken? Fix it. I should apologize in between. Every commit, it's basically apologize because I break the machine of something. And commit it again. And repeat with the next step. So that's the motivation that leads me, okay, why do I want to change something? Why changing something is hard and break something? That's what's coming afterward. What are those dragons? So let's go to representation of addresses and routes, which is basically the blocks to represent, to imagine this abstraction that is a network. No questions so far? Okay. Well, maybe you're a bit familiar with that. What is an address? What do we use addresses for? This might be superfluous or trivial for some people. But I wrote on the left side of this slide 2 questions. And those 2 questions are really interesting because everywhere in the kernel, in the network park, when you want or you access somehow the representation of a network address, it's to ask one of those 2 questions. Identify peer, that's who should receive, or who supposedly sent the packet. That's a question. Basically to know, is it for me? Did you send that cat to me? And the second question is, where should I send the answer? Where should I send something? On the right-hand side, you see a picture representing a fixed header of the version 4 of the IP protocol. I will be concentrating on the code touching the IP protocol. And as example, the version 4, we can talk about the version 6, but I will prefer to keep that for later. An interesting point, I put in red the information that correspond to the question on the left. And this chunk of this representation of chunk of data, we cannot choose to change it. That's something that we have to deal with. That's really interesting. That as an operating system developer, as an architect, you can decide to represent things as you want. Why a table is this size? Why do you want to paint this color? It leads to a lot of funny back shading. That's interesting. But that we cannot change it. So we have to work with that. Now, in opposition to this, before the opposition, what happened in your kernel? What's happened in your operating system when you receive a packet? What happened when you send a packet? In order to give support to my words, I draw a simple picture that I will be illustrating with more programming a question later on. On the left-hand side, you see that, well, you have some input. I won't go into detail how does it work, but you have a packet. Your machine has a packet. The question you are asking is this packet for me? Well, because if it's for you, you want to look at it. That's what I put on the right-hand side. So you deliver the packet. By delivering, I mean you transmit the packet to whoever is supposed to receive it on your operating system, which application. But there are a lot of possibilities. But what's interesting here is the question, is it for me? This question, I join it to the identity point that I previously presented on the side. Now, if it's not for you, and for some reason you appear to want to send this packet to another computer, I don't know if some of you have your router equipment, if you use a, I don't know, Wi-Fi access point in conferences or in your home, well, they certainly send this packet to somebody else. That's what we call forwarding. So do you ask the question, well, I'm supposed to forward this packet. There's a various question to say yes or no. And if you appear to be able or to want to forward this packet, then you have to say, well, but where? Typically, when you plug your computer to a switch, a router, it has multiple ports. How does it know which port you're going to send the packet? Is it supposed to send to all? We can go to history about that. But as an operating system, OpenBSD has a mechanism to select where he's going to send it. If you have only one cable, basic traditional laptop, it will be easy because you will be receiving always from this cable and sending to this cable. And that's basically what I'm writing on the left-hand side when I see send. If you're sending a packet, if you're sending information, well, you just have to pick, well, which port, which interface I'm going to send to, and send it. Now, this question, which interface you want to use, is basically the question, where I am you supposed to? Which route do you want to take, or do you want to tell the packet to take? That's the second question that are inside this forwarding path. Now, these questions are present in different places in the kernel. But I'm going to concentrate on this particular code path because that's what critical performance, that code is executed for every packet you are passing through. So if that code is slow, well, you will have a slow forwarding machine. And if you want to make it fast, you have to understand how it works. That's what we are going to talk about. Now, I show the representation of the IP packet IP header. How is it represented in your kernel? I hope you're not scared with some C structure declaration with some love from Berkeley. But in your kernel, and I come back a bit later, I think this structure got introduced in '85, something around that. And it's basically containing the information that you want to match to the packet you're going to receive. Is this an address that it's configured on an interface on your system? That's the first field. Even if you don't understand the C semantic, you can read the comment that's quite explicit. Is it a destination address? If you have a point-to-point interface, that's for point-to-point. Here we are, it's a reuse trick if you appear to have a broadcast address configured on this interface that is full of Dragon, for example. That's something that, well, people want to save space at some point, so no need to add another field. Now, when you have some generic code that deals with addresses, and that might know if this field is representing a destination address or a broadcast address, because it's the same field. So there you can have a lot of crash. The rest of the field are quite self-explainable. One interesting point, and then we come back to that right after, is that you have a pointer. That means that you have a link that shows you which interface this address is configured on. When you do ifconfig, the name of your interface, that address, maybe some of you do, well, that's the interface, let's say EM0, the IFP that is used in our language of developer. And the address that you will put on this interface command will end up encoded in this field. So how does that glue together to draw a picture in the memory representation of your kernel? Well, let's start simple. Start simple. You boot your computer. Of course, what I'm talking here, I forgot to mention that previously, right? I'm obviously talking about how is it in OpenBSD. But most of it applied to all of the BSD system because they share the same stack, right? With some detail. I will mention right now. So you boot your machine. You boot your machine. It appears that you have a network interface in your machine. At least one, let's say. We're in 2013. What this network interface is here represented by the EFP symbol, right? IFP. On top of that, you have what I call the interface list. This square rectangle means that this list is a global structure. Name of the slide is global data structure. Which element or list, trees, pointing to object can be reached from anywhere in your kernel. That's really similar that the kernel is just a simple program with global variable, let's say. So you have a global variable that you can use to reach interface. This one is the interface list, or a list of interface. So you have an interface, and it's in the list. Now, this slide represents more or less what was in OpenBSD 5.4 and before, where every time you had an interface, you had what I wrote it a link layer address, a physical address associated to this interface. No matter which kind of interface, no matter if this interface really has a physical interface, it was present. It was always present. It was always present, so it's like one-to-one mapping with your interface, right? You have an interface, you have a link layer address. The arrow that are represented there, so you see the arrow that comes from the interface back to the interface, from the address back to the interface, is this field that you see here, the back pointer to the interface. I hope I'm not too confusing. Don't hesitate to stop me if I am. Now, the interesting point is that you see that there is a red arrow starting from the interface and going to the address. This represents a list of addresses configured on the interface, right? So you boot your system. You have an interface. You put it in the list. You add a physical address, and you put it on the list of the interface, right? Now, since this address, this link layer address, let's say, is represented like any other address in OpenBSD, and it's still true right now. No, it's no longer true since some months, but in 5.4 it was true. It was also ending up in a red-black tree, which is also a square, well, rectangle, which means it's another global data structure. That's something you can access from anywhere. Any kind of network code can use it to reach your address. So what we see here is that if you start using any kind of code in your kernel, you can find the representation of your address by using two different structures. Either you say, well, let's look at the interface I have on the list and which address they have on every interface. Or, well, look at the tree, what address did we put in that? That's representation of an interface without address, right? No question? Okay, let's put an address on this interface. That happened. It's a bit scary. And I don't have a picture when I work with that. It's almost... Well, there's a lot of stuff missing. But then I will scare everybody. Okay, so now we are adding an IP address, right? You did your ifconfig command. So what I'm calling ifile on the bottom of the slide is the representation that I've just shown before that will contain the address you just configure on your interface. This ifile, as you see, there is a red arrow pointing to it. That means that it is also in the list of addresses of your interface. It's part of the interface. You did ifconfig em0 blah blah, then this blah blah is on em0 list. Since it's an address, it's also appearing in the tree. All the address, we put them there. Since it's an IP address, well, we find another structure. Because it's easier for us to work with that. So we have another global structure that we can reach from anywhere that points to this address. And now, since you want to use this address in the real world, you want to say, well, I would like to reach the EuroBSDcon website. So you say, well, where should I send this packet so that it reaches a EuroBSDcon server hosting the website? Well, certainly you should use the address that's configured, because if you have only one address, it's probably the good one. But the mechanism that makes the decision of destination, one of the two questions I was presenting before, is done through the routing table. So the routing table contains root entry that I wrote there as RT entry. Those entries say, well, it's just a path, it's just a route, go there. But what's interesting in our point is that those root entry are pointing also to the address, because that's the address you want to use in the end. Now, it appears that the routing table is also a rectangle. So if you followed and not asleep after lunch, you get that it's also a global structure. That's what I'm going to talk about. Why is that interesting? Because when you look at this picture, I don't know how familiar you are with multiprocessor development, concurrence history. But the first problem that you have is that, well, if I have so many structures where I have the data of my address, then first of all, I have to make sure that they are coherent. Because if one doesn't get the change that I just did on my address, what will happen to my network? Well, you will find dragons on your operating system. Something will break. And that was already a point. We are not executing, accessing this kind of resources in parallel. But even for configuring these resources, configuring these global data structures, it's complicated. I won't mention names, drivers, but we can talk about it with beers. Now, apart from coherency, as soon as you're going to say, well, I want to add a new address, and at the same time ask the question, which route should I use to send this packet? You might end up modifying or accessing one of those 4 global structures at the same time and potentially crashing your kernel. I won't go into the detail of why, but the point is you have to protect somehow those global states when you're working in multiple, in parallel programs. So the question is, well, okay, start looking at that without pictures. It's an incomplete pictures, Claudio said, and he's right. Now, if we look just at that and we say, well, I have to make that code accessing to that work in parallel. Well, I wish me good luck, because I'm already scared just as looking at the picture. So the question was, well, if I have to make that code written in the 80s run in parallel, would it be better first to start to simplify it? Because you see, you have 4 different ways to reach to your address. Do you really need 4 different ways? Well, the answer is no. Otherwise, I wouldn't be giving a talk here. And that's what I'm going to explain. But most importantly, before starting to say, well, which one of them we can use, let's say where they're used. So you have 4 rectangles, 4 global structure. You remember this picture? Well, the first question we were asking is it for me, the packet? Identifying who is the receiver of a packet. Well, to do that, we use 3 of the structure. This is mainly done in the function for the version 4 of the IP protocol in IP input. Once again, that's represent how OpenBSD 5.4, what was in OpenBSD 5.4. I will come to what's now, right? This is, I didn't really check, but I encourage people from the other BSD to go look, and I don't know how true it is, but I assume it's mostly the same. Now, if you're supposed to forward the packet, you're going to access one global structure. And when you're sending a packet, at least 3 of them. Now, you have a star here, because in the case of you forwarding, you're also sending, obviously. But you won't access the routing table twice. It's one or the other. So I put it here because you might just want to send a packet, right? In this case, you will use the routing table in the select interface block that we see here, that is represented by the IP output function. Excuse me? Yeah, well, we could include it, but it's due to the question to make it clear for the code, right? So we have the picture of how scary it is, of at least one small piece, how scary it is. Now, we mostly know in this particular function or piece of code, which is executed when you forward the packet, where they are accessed. That means that they're also accessed in different code paths. But I only have 45 minutes. Now, the question is, what can we do? What has been done? How did that change? And sadly, well, what break in the meantime? So, first question is, we have 4 of this global structure. How can we reduce the number? To how many of them? Which one should we pick? Now it's quite easy to say because the work has been mostly completely done. So I wrote down some rules that might be useful for other people, I don't know, about the global list. The first point I explained when I was showing the representation of a kernel that just boot without configured address is that the link layer address, no matter what kind of interface you have, no matter if it's a real interface or not, no matter if it has a link layer address or not, has a memory chunk which is used by the kernel to represent something that should be the link layer address. So if you always have it, why would you look for it? Because you know it will be present. Why would you have to search through a list? Where is it? It's there. Don't worry. So just remove the list lookup that look for it. First rule. That's quite easy to do and quite interesting. There's an interesting point that about the design of socket or DL that if you're using also userland, used to do userland networking programming or works with daemons, it's an interesting API to take an example of something that you should not do. I won't go into the detail, but that's quite interesting over a beer. The second rule is, well, I show on the picture that you have these red arrows, right? So if you already know which IFP, by IFP I mean interface, right? You remember where you port, where you're going to plug your cable into. The packet is coming through or you're supposed to send it to, right? If you already know that, why would you lose to look in all the possible interface in your system to find an address that you know that is on this, configured on this IFP, on this interface? Well, second rule just uses local list, as I named them. There's something that might be, I don't know, obvious for some people, but when you work with code that is older than you are, sometimes with carry commit messages, you end up looking at functions that you have really no idea why they're doing a loop. And sometimes you can just kill them. So you have to go back in time, look in the CSRG archives, say, why is that here? Why did they write that in the first time? Oh, but it's not needed. Well, remove that. When I see this kind of chunk, whoa, I'm really, really late. I will be late. When I see this kind of chunk, I say, well, thankfully, I didn't go deeply into protecting those chunks because you can simply remove them. And finally, and I will explain why a bit later, if you don't have to use one list, just use the interface list. If it has to be one, well, just reduce to one. So here you have some example of what have been changed in some function. You can go look at it. Coming to the interface list, I'll be a bit short about that. But what's interesting is the history of this structure that represents all the interface that you have on your system. When it was, when I look at the history of the BSD code, I saw that in 81, every interface has only one address. So you have a perfect match between looking at your interface, you already got your address, like I was saying for the link layer address. And actually, those functions that I used to iterate over this list were not named IFA, but if, like interface. What's really interesting is that when you look at this code, none of this code wants an address. They want to know the interface which has address, or they want to know if an interface has an address. So we have a lot of useless code because this API got written for something totally differently that is used for. Now, when in 85, the structure that I presented before, that's representing an address, got introduced, well, the loop that used to be just iterating over one list of interface matching addresses, that's got changed into a loop iterating over the interface and a loop for each interface iterating over addresses, which in some system right now, when you have a lot of interface, a lot of addresses, is really slow looking on this list. That's why in 2010, a red-black tree was introduced to make this lookup faster. An interesting point is the other structure I was talking about, the per protocol address. That's the name of the IPv4 version. Also got introduced in 85. Basically, I couldn't find the reason why. It's really easier to write code when you know that all the IP addresses are there instead of all the addresses. This list is used in the version for the protocol, and this one too that got replaced by the red-black tree, as I presented before on the slide. When you decide to forward a packet, to know, is it my address? One interesting point is that when the IPv6 got integrated and people explained the choice they did in 99, they say, we will use the routing table for that, to know if the address that's the destination of the packet is our system or not. They use basically a hack to do that. But that's where we are now in OpenBSD. The solution or the evolution of the network hack is to use the routing table for all those operations regarding searching an address. Routing tables are not really used for that, or were not designed for that, but we can use that. So what I did is consolidate what I call the loopback hack that came implemented. That's to say, well, if this address is configured on your system, that it's somehow related to your loopback address. I hope loopback address, the low 0 or something. The consolidation came with an indication with flag. Okay, this route represents a local address, so it got a local flag. For IPv4, we need also the information of the broadcast addresses that are associated to your unicast addresses. So we also have this information, like we had route to subnets. Now, with this change, we can go to only one global structure. So no problem of coherency between the structure. Only one focus that we have to protect. Then we have to think about how to use it and correctly use it to be run on multiple CPU. And the tests that we run in order to choose the solution, and that were also confirmed by the paper talking about the red-black tree, or the paper that was written from the KM guy, that is not slower, faster than the actual tree that we are using for looking addresses. Since I don't have time, I will skip this slide. That was a good example of why you need to change the structure. And I will get directly to some related changes because I'm here focusing on the forwarding path and the global structure. But thinking about how to make a subsystem or an entire kernel, I would say MP safe or easier to run on multiple CPU, can lead you to rethink completely the design of those subsystems, of those programs. So as I said before, removing the loops for the link layer address means that we can simply remove the link layer address from any list. That's information that I don't have to put in the routing table. I already mentioned that there were many dragons in there, so I won't expand. The option that was described in TCP/IP volume 2, I guess, of so-don't routes that you can set on socket, which is defined as used to bypass the routing table, is just ignored on OpenBSD right now because we don't want to bypass the routing table anymore. We just want to use the routing table. We can re-implement it differently, but it's easier to get rid of the old code. And if somebody really needs that, just come talk to me, and we'll see what we can do. I doubt it. Now, for a reason regarding dangling pointers, when you try, it's really related to what Ted, you talked this morning, right? You try to access the memory of something that got removed or replaced. And that is really easy to trigger if you start having multiple processors, because one might remove something and the other wants to access at the same time. So there is some trick. That's basically some computer science solution. And one of them was to use a big table where every index of interface, every chunk in this table hold the pointer to an interface. So we don't need to use the pointer directly. We just give an index, give a token, and get back a pointer. If the pointer gets cleared, that means that the object is gone. If not, that means it's here. That is interesting because we already have a lot of pointers everywhere. Because when this subsystem was written, things were not so plug and play. There were only one CPU. It was much more easier to maintain coherency. And finally, I replaced some function that were using a global buffer to use a buffer pass on the stack. That's the last point of this slide. Now where we are after all this change? Well, it's basically the conclusion of the work, right? And we are almost on time. That's how it looks like now. I don't know if you remember the previous scary representation, right? We were here. And we are here, right? You don't need to understand what's on the slide or what links, but it's simpler. It looks simpler. Now, where this is used, so you see that you have two rectangles, right? Routing table and the interface list. Well, in the chunk of code that I was analyzing before, well, we are using that. And the star mean that you are using here or there. So we move from 3 global structure here and basically 3 here to just 1 in the whole code path. I'm almost not lying. Some bits are not yet integrated in OpenBSD, right? This is what I have in my development environment. Now, you can look at the code if you're interested on the mailing list we use to share and to code review that. You can even review it if you're not a developer. That's really interesting. You can run it. You can test it. There's still, the second point means that there's still a link between the interface and the routing entry it's not removed yet, but that's a part of the removal of the KEMS hack. And I was lying when I was saying there's only one lookup. I'm sorry. With the diff that I sent, we are actually in the forwarding case doing one lookup here and another one here. But that's just some code shuffling to have only one instead of 2. Hopefully that will be integrated in 5.7. Well, depends how many dragons this will find, so I hope you will test it. Concluding, we are late, but let's go for a conclusion. So, refactoring 30 years old code is hard. But, well, pretty good story that you know which person is to blame. So you will be able, or maybe some of you on future developers will blame me later for having done things that are not adapted to future software. Hopefully, BSD will still be used. Now, since the number of people working on this refactoring is me and myself, it's quite difficult to get feedback from people. So I find dragons. Every of those chains that are presented break at least one setup. It's not a feature, it's not interesting, it's not cool. Nobody wants to look at it, and when they look at it, they know that will break something. So that's quite hard. That's why understanding what you're changing is important, and I hope that what I presented here as a slide, that can be a complement to the design of the networking stack on the BSD kernel is interesting, because you have how basically it was in the 80s and how it's evolving or how it is right now. Sadly, there's still a lot of work to do, and the picture that you've seen are really simple compared to what's missing. So we'll find a lot of dragon. Oh, I'm too fast. That's it. So if you have any question, I'll try to answer them.
A year ago, I read a paper about the multipath OpenBSD support and route preferences. In the end of the paper, people say it's very good, but it's very dangerous. There are many dragons. I would like to know if has changed.
Something has changed, but there's still a lot of dragons. If you want to have more detail about that, I recommend you to talk with Claudio, that is trying to tame those dragons too. I'm not the expert on that subject. I'm just here to put more pressure on the subsystem to make it break. Actually, the citation on the slide is coming from this area of the code. So that might answer your question. Yes,
Any further questions? Yeah.
Do you have any test results after you make these changes? I mean, how fast is it now? And what actually, how long it took to make these changes? And you know, what pending changes do you have? You said it will be released in 1 year from today, hopefully.
Okay, so three questions at a time.
Yeah.
The first one was, what can you, performance testers. The performance testers I have are here to make sure that it's not slower. No, not at least, because I'm not interested right now into gaining performances. I'm interested into refactoring the code and simplifying the code so that it makes easier to gain performances. Not do it twice at the same time. That will be horrible. But most of the function that I change, well, most of them, some of them, I was talking about useless lookups. So in particular cases, for example, with the carb driver, you have performance improvement because you do less lookups. But that's really insignificant. That's 1-2%. It's not the aim of the work, right? You say, what I was saying about when it will be integrated, right? The slide about where it is right now is a slide that where how it will be when the diff I sent beginning of the week will be integrated. Hopefully in the next weeks or months, right? That's answer your question? Any other question? Don't be shy.
Gone. Let's thank our speaker then.
Thank you.